Tad, thanks. That was a fantastic presentation, and I'm sure I join everybody in expressing my appreciation for the pragmatism and practical applications that you set out there for us as part of the technology development pathway for medical nanobots. That was great. Our next speaker on the track of technology development pathways for medical nanobots is Dr. Ralph Merkle. Dr. Merkle received his PhD from Stanford University, where he co-invented public key cryptography. He was a recipient of the 1998 Feynman Prize for Nanotechnology, co-recipient of the ACM's Kanellakis Award for Theory and Practice, and recipient of the 2000 RSA Award in Mathematics. Dr. Merkle holds 14 patents and has really achieved the status, I don't want to embarrass him too much, but I would say is really as a giant in the field of nanotechnology. He's certainly been a guru to whom I've looked and learned from his publications over the years, and it's just an immense pleasure to welcome you here, Ralph, to this conference. Thank you.
Well, thank you very much for that very kind introduction. And I should also like to put in a plug. The last speaker was mentioning Robert Freitas and the work he's done on nanomedicine, and I would put in a plug for that. It's excellent work. If you haven't seen it, I would recommend it. And also the other thing I'd recommend, how many people have read Feynman's There's Plenty of Room at the Bottom? Okay, most. Okay, so the ones who haven't read it, it's on the web. Just Google Feynman, There's Plenty of Room at the Bottom, and you'll find an excellent paper, and you'll love it, and you'll have a great time doing it. Okay. So, diamond mechanosynthesis is a path to medical nanorobots. We've been hearing so far about the capabilities of nanorobotic devices, and if we could build them, they would do this, that, and the other, and how do we coordinate them, and if you have large numbers of them, there are issues involved. So what I'd like to focus on primarily is, how are we going to do this? What's involved exactly in making this happen? And before I go into the talk, I would like to put up a few URLs, www.molecularassembler.com/nanofactory. That's a website that I and Robert Freitas have been working on, which discusses how it is you go about building nanodevices of all varieties, medical nanodevices being particularly included. And also nanomedicine.com, which has a website that discusses the nanomedicine book series and provides you with a lot of information about nanomedical issues. So the long-term goal is very simple: design and build a diamond nanofactory. Okay, so some framing, some context. If you think about what we're talking about, at some fundamental level, we're talking about the relationship between things that we care about, such as our health and our wealth, and atoms. And when you think about it for a moment, you realize that how atoms are arranged is very important. So for example, if you rearrange the atoms in a hunk of coal, you get diamond. So that's kind of valuable. How the atoms are arranged is important. Similarly, if you rearrange the atoms in a computer chip, if you rearrange the atoms in sand, you get a computer chip. So same atoms, different arrangement, very different in terms of our ability to use them and their value to us. Sand is cheap. We don't actually have a lot of value on it. Computer chips are valuable, and we use them for many things. And finally, of course, in the case of health, how our atoms are arranged is very important to us. Atoms badly arranged are unhealthy, ill, even dead. Atoms properly arranged are then healthy, happy, out bicycling, having a good time. So the general point of this slide is simple. It makes a big difference how we arrange atoms, and what we would like to be able to do is arrange atoms at will. Now, if you look experimentally, you find that for some time now, we have been able to arrange atoms on a surface. So here is an illustration of research work arranging atoms on a surface. These particular atoms are cobalt atoms on a copper surface. It's at very low temperature in using a scanning tunneling microscope in ultra-high vacuum. So under limited circumstances, we can arrange atoms the way we want. And in particular, in 2 dimensions at low temperature, we have a pretty good track record in a few specialized cases of being able to do this. The broader principle is that we should be able to arrange, The broader principle is that we should be able to arrange atoms in most of the ways permitted by physical law. We should be able to achieve a much wider flexibility in how we arrange atoms. We have not yet experimentally demonstrated this capability, but there's a lot of theoretical work that says, you know, these things called atoms can be arranged in a whole bunch of ways, and we ought to be able to achieve this control over the arrangement of atoms, and that will let us do quite a few things. So I'll be talking more specifically about diamond. Diamond, of course, is made from hydrogen and carbon. Primarily carbon. Hydrogen, of course, terminates the surface. When you talk about small parts, there's a lot of surface, so the hydrogen becomes very important. And the reason I'll be talking about diamond is simple. If you ask about materials properties, if you ask about strength or lightness or transparency or band gap for electronic purposes or thermal property, go down the list of materials properties. By the way, you're not supposed to actually read all of the items on this slide. You're supposed to be impressed at the large number of them. Diamond is wonderful in a large number of different ways, and this sort of says, yes, there are many properties that if you look at them, diamond is wonderful. So when you come to the point of saying, you know, the important thing in the future is not going to be, you know, this, that, or the other structure. The important thing shifts to not whether or not we can build something. The important question shifts to, okay, what do we want to build? And diamond pops up to the top of the list because diamond is wonderful in a lot of respects. So once you accept that premise, that diamond is a good thing to build, then you start exploring what you could build. This is a theoretical structure. It has not been built, but as far as we can tell, if you built it, it would form a very nice bearing. It has 2 parts. It has an inside and an outside. The inside is simply a flat piece of diamond bent into a tube. The outside is another flat piece of diamond bent into a bigger tube. You take the smaller tube, you put it in the bigger tube, throw the resulting theoretical structure into your favorite computational chemistry tool, and the result is, gee, it looks like if we could build this, it ought to work, it ought to form a fine bearing. This is something that came out of NASA Ames. This is gears. You take some bucky tubes, you put teeth on them, you rotate them. They have some molecular dynamics simulations showing them chugging along, rotating, and doing other useful things. Again, this is one of those things where we can't build it today, but it looks like we should be able to build it in the future. This one is more colorful. Instead of using just hydrogen and carbon, this uses a lot of other elements. And ultimately, we want to be able to achieve that capability. You might have seen this because this is colorful, the press likes it. So if you're doing a magazine run, then this has color. Hydrocarbon is black and white. It's boring. So you take the colorful one, you stick it in and say, here's an example of a molecular machine. It's actually harder to build in the sense that you require a greater understanding of a larger number of elements. You have to have more complex synthetic capabilities. But it's more interesting if you put it on the printed page, and as a consequence, it's more popular. And if you take a look in the lower right-hand corner, you'll see a little colorful dot. That shows the size of that planetary gear I was showing in the last slide. And this is a theoretical proposal for a molecular robotic arm. And it has some millions of atoms in it. It has not been designed in molecular detail, but it could be. Provided with an appropriate budget, one could go ahead and design a device with millions of atoms on the robotic scale that should work if you could build it. I think a lot of people accept the fact that, yes, if you could build this, this would be a successful robotic arm, and then the question that crops up is, okay, how are we going to go about building such a thing? And as you get into larger and larger devices that you could build out of sort of diamond and materials related to that, one of them is the respirocyte. And the respirocyte is absolutely fascinating. It's a conceptually simple proposal. You build a tank, and if you build a tank out of diamond, you can have a very strong tank, and you put oxygen in it to, say, 1,000 atmospheres. Now, if the tank is on the order of a micron or 2 microns in size, and it's small, it can float around in the circulatory system. And if you have some control device that allows you to meter out the oxygen at some appropriate rate, then such a device could provide oxygen to the tissues. And if you go through some basic calculations, you find that at 1,000 atmospheres, your device can hold hundreds of times more oxygen per unit volume than red blood cells. So this artificial red blood cell would let you do things that normal red blood cells would be hard-pressed to do in a quantitative sense. If you had a therapeutic dose of these devices injected into your body, they could support your metabolism for on the order of an hour or more, particularly if they also incorporate a way of uptaking CO2, which I won't go into detail, but basically, yes, you can have binding sites that bind to CO2 and then can bring that into the tank. So if you dispense oxygen and absorb CO2, then you can support metabolism for a few hours, which means, for example, that if you had been injected with a dose of these devices, then if you had a heart attack, you were at risk for a heart attack, you were injected with these devices, and you said, oh my gosh, my heart has stopped, you could then call your doctor and say, doctor, my heart has stopped, what should I do? As opposed to the usual scenario, which is you fall over and bad things happen. So if you have time, doctor, my heart has stopped, well, you should come on down to the hospital right away because, you know, you're on the clock now, so we need to respond fairly rapidly. Okay, I'll be there, it'll take me 20 minutes. You've now got time to respond, time to diagnose what's going on, and time to heal the injuries and actually walk away from the event without the kind of damage that we see today. So that's the idea of an artificial red blood cell, and it looks like it would be very useful. So this is just an illustration of a conceptually simple device which would have high utility in medical applications, and it looks like we need some sort of synthetic capability that we currently don't have in order to build this. Okay, so what's going to happen? How do you build molecular nanodevices? And in particular, we're talking about diamond. The reason we focused on diamond is it makes life simple. If you talk about designing things that have 100 different elements in them, because there are almost, 100 natural elements. There are over 100 elements in the periodic table. Some of them are artificial. That's a lot of chemistry. You have to do a lot of analysis. You have to think about a lot of things. If you confine yourself to hydrogen and carbon, life becomes a lot simpler. And in fact, in a paper which is coming out hopefully this month in the Journal of Computational and Theoretical Nanoscience, Rob Freitas and I are looking at the reactions involved in synthesizing diamond, and we've proposed that we use hydrogen, carbon, and we've added one additional element, germanium, in order to make the synthesis feasible and flow very nicely. So here are the tools. So the claim is, if you're going to build molecular structures, you need molecular tools. If you are going to use molecular tools, you have to describe what those molecular tools are, and you have to describe the specific reactions that take place when you use those molecular tools. So here are the molecular tools. There are 9 of them. And those particular molecular tools are supposed to be at the tip of something that would look like a scanning probe microscope or the tip of that robotic arm that we were looking at. So these tools are meant to be held and positioned and applied to a growing diamond surface. And I won't go into the specific details, but what you'll note is that these tools, well, there seem to be black atoms, which are carbon, white atoms, which are hydrogen, and yellow atoms, which are germanium. So these tools are built out of 3 elements, and we have a set of reactions described in loving detail in the paper that say if you have this set of tools, you can take raw feedstock molecules and use this set of tools to synthesize another set of tools. And also synthesize various interesting diamond structures, diamonds, fullerenes, Bucky tubes, Lons Delight, and of course a variety of interesting organic compounds, hydrocarbons compounds. And to give you a flavor for the kind of analysis we did, we would go through various reactions. This is the hydrogen abstraction tool. This particular tool has a high affinity for hydrogen. And you bring the tool up to the surface. You pluck off an individual hydrogen. And as a consequence, you now have a radical site where previously you had a stable bit of diamond. And if you look at that reaction, we did the analysis using standard computational chemistry software. And if you look at it, you find that that particular reaction is favored by about 1.59 electron volts, which is a number you get, like I say, by running it through your favorite computational chemistry package. You can also do the reverse of that. You can have a hydrogen donation tool. If you have a hydrogen which is sticking to a germanium, that's a weaker bond. If you bring that tool up to a dangling bond on the surface, then the hydrogen will jump off of the germanium and onto the carbon, so you now can donate a hydrogen to a dangling bond on a diamond surface using that particular tool. And then we have a tool or a sequence of reactions involving a tool that allows you to deposit a carbon atom on a surface. You take an inert surface on the left, you pluck off a hydrogen with a hydrogen abstraction tool. You then bring in a carbon atom, which is on a tool which is bonded to a germanium atom. That carbon atom is reactive. The carbon atom on the tool has a dangling bond. The surface has a dangling bond. You bring the tool up. The tool interacts with the surface. The 2 dangling bonds bond. You then pull the tool back. The tool, remember, has a germanium-carbon bond. Germanium-carbon bonds are weaker than carbon-carbon bonds. So when you pull the tool back, the carbon atom wants to stay with the surface rather than going with the germanium tool. And then now that you've got your carbon atom on the surface, the carbon atom on the surface has a dangling bond. You can stabilize that dangling bond by donating a hydrogen. And at the end of the sequence, you have added 1 carbon atom to the surface. The surface started out in an inert hydrogenated state, and the surface ends up in an inert hydrogenated state, and you've added 1 carbon atom at a site-specific site. So if you keep this up, you can build a lot of things. Okay, so I won't go into the details. Suffice it to say we've proposed 9 tools. We've got 100% process closure. In other words, if you've got a set of tools, you can build another set of tools. We're using simple feedstocks like ethylene and germane. We have a total of 65 reaction sequences. So there's a lot of reaction sequences. A lot in the sense of, it's more than 3 or 5. But compared with the complexity of a lot of systems, this is very straightforward. This is, 2 guys working for 3 years. And that's the kind of complexity you can deal with. There are actually about 328 independent reaction steps. So each reaction sequence shows a useful thing you can do, and each reaction sequence is a bunch of individual reactions. And each and every reaction has been analyzed using a standard program called Gaussian. For any of you who are familiar with the computational chemistry world, Gaussian is a standard computational chemistry package. And it took about 100,000 hours on sort of standard computers, sort of standard commercially available computers. So that was the work we did. And basically, now that we've done that, now that we've got a set of reactions, we are, of course, looking at the next logical step. The next logical step is, if we have a set of reactions that should work in theory, how do we put those reactions into a program that will let us develop those capabilities in practice, and then step forward from being able to do it on a small scale with a few atoms to being able to do it on a large scale with many atoms. Okay, and what does this have to do with nanomedicine? Well, Disease and ill health are caused largely by damage at the molecular and cellular level. And today's surgical tools are just too big to deal with that kind of damage. In the future, we'll have fleets of surgical tools, molecular both in size and precision, and we'll have computers much smaller than a single cell to guide those tools. So to give you some size scales here, remember that robotic arm? So that robotic arm was about 100 nanometers tall, so that's about the size of that little red cylinder in the upper right. And in the middle you see a mitochondrion. A mitochondrion is a subcellular organelle. And to the right you see the approximate size of an 8-bit computer. And this is an 8-bit computer that's using molecular mechanical logic, which is slightly different from electronic logic. Electronic logic would be somewhat larger. Molecular mechanical logic can be smaller because nuclei have a better defined position than electrons. Electrons tend to fuzz out and jump around. Nuclei are less prone to this. So that gives you a rough size compared with a mitochondrion. And then if you back away a bit and look at a, quote, typical, unquote, cell, if there is such a thing, then you find the mitochondrion is small in comparison with a cell, and the robotic arm and the molecular computer are vanishingly small, so you could literally put hundreds of thousands of these gadgets inside a single cell, and the cell wouldn't notice. So we're talking about molecular devices under programmatic control that have very specific sensors and actuators that we could build in the coming decades that would be programmable to do useful tasks, and then you get to discuss the various useful tasks that such devices would be able to do. And that's the end of the talk. Thank you very much.